Next, we are going to learn about linear momentum. We are going to represent momentum using lowercase p, and if it's for the center of mass of the object, we're going to use capital P. So it's important that the how you use the letters, okay? So mainly we will look at an alternate version of Newton's laws, and it will be useful to study the collisions. I am planning to skip some of the collision parts. I'm going to give you a brief description of momentum conservation, and a little bit of collisions, but we are going to spend more time on angular momentum. So this linear momentum concept is so important that we are going to build up on it. And rotational stuff is going to be a little bit more complicated because of the cross products and vector algebras. Okay, so it is important to note that this concept is just a variation of Newton's law, and it's nothing different, okay? We're not using a new law. And momentum of a particle is given as P is for momentum, again, that's lowercase for a particle. And m is the mass of the particle, and v is the velocity of the particle. So p and v are bolded. That means p and v are vectors. So mainly, since mass is a scalar, that's the scaling factor. So you're multiplying mass with the velocity vector. That gives you the momentum vector. Okay, so momentum is also a vector. And p is called a linear momentum, and is the product of the mass and the velocity vector. So again, p is a vector. In unit vector notation, you can write it as px I hat plus py j hat plus pz k hat. And since each p components can be written in terms of mv, and using the correct labeling, we can write this momentum form in this form, right? And again, p always points the same direction as v, because we know that, again, p vector is mv. Instead of bolding, we can use the arrows, right? When we're writing, that's how we write things. So p and v points the same direction because mass is always positive. Units, again, this mass times velocity. Mass is kilograms, right? And the speed is, or the velocity is, meters per second. So it's kilogram meters per second. There's no special unit. So you're just going to think about the definition of momentum, mass times velocity, and figure out the unit from there. In English units, it would be slug, would be the mass, and the velocity would be feet per second. So it would be slug feet per second. And instead of writing this equation like this, like fully, we are going to kind of look into separately. So px is mvx, py is mvy, and pz is mbz. So like you can see it on this side. Okay, so there are really three equations that you can write if there are three dimensions for the problem. And so now we'll look at how this concept is related to the second law. So we're starting with the definition of momentum. P is equal to mv. Again, p and v are bolded because they're vectors. Now let's take the derivative with respect to time, both sides. P becomes dp over dt. And when you take the derivative of mv, since m is constant, you can take it out of that derivation. So that's why you have m out of that derivative. And you have dp over dt equals to m times dv over dt. But what is dv over dt? That's the change in velocity over time, right? That's the definition of acceleration. So that's what we're writing here. And then that will mean dp over dt becomes m times a. So mass times acceleration. Okay? What is mass times acceleration? It's from second law. We know that that's the sum of forces. So when you replace that with the ma with sum of forces and kind of flip the sides, this is the equation you're getting. Sum of net force acting on an object is equal to its change in its momentum, linear momentum with time. Okay? This means if there's no net force acting on the object, the momentum is not changing. It's constant, okay? And then that kind of brings us to the momentum conservation. Okay, so that kind of is very important, and this tells us the condition. We will discuss this in detail. So first, this says the net force acting on an object is equal to the rate of change of the object's momentum. Okay, that's kind of how you read this equation. And this is the second law, but it's in momentum form. And this is the way that Newton postulated. So that wasn't sum of F equals to ma, it was in this form. But writing dp over dt is just another way of writing mass times acceleration. Okay, so they're like, the forms are the same. This is not a new equation. As three scalar equations, we could write for the x, we can say sum of fx equals to dpx over dt. And that's equal to px becomes mvx, so you can substitute that. And you can do that for the other three equations as well. And again, if you check the equation sheet, you'll find those equations. Okay, so let's go down. Now this is for particle. And again, small case p is for particle, okay? It's not a distributed mass. And now what about how do we find momentum of a distributed mass? So we can modify the results about slightly to work for a distributed mass. First thing, we are going to use capital P, and that's going to mean that the object is not a particle. Okay, so when you do that, that means the velocity, the acceleration, whatever you're using, or position, they are only true for center of mass point. Okay, so we are clearly labeling that here. So P is equal to mv, and that P becomes capital P because it's for a distributed mass, and capital M is for the total mass of the entire object, and V, center of mass, that's the velocity of the center of mass point. Again, this is a vector equation. You can write this in three components using I, J, and K. I is for x-axis, J for y-axis, and K for z-axis. And you can see that velocity components are consistent. Next to I, we have x component of the center of mass velocity, and so forth. Capital P, again, and it's bolded, is the linear momentum for the distributed mass. And again, we used P for power before. Power is not a vector, first of all, but we use the same letter. So make sure when you look at the equation sheet, you distinguish between power and momentum. Okay, and capital P again is for distributed mass, but that is linear momentum. Capital M is the total mass, and V, center of mass, is the velocity of the center of mass. So another way of postulate sum of F is equal to MA, center of mass, is simply saying instead of MA, we have dP over dt, but again, this P is capital because it's for the non-particle object, okay? And in components forms, again, you can split it in three. You just gotta pay attention to labeling. Put the x's for the vectors. F is a vector, P is a vector, velocity is a vector. So we have those x components here, right, and there. And once you are consistent like that, and acceleration is also a vector, so all of those should take x components. The rest is like mass in here is a scalar, so it doesn't have any components. And you do the same thing for y-axis, y components, and then z components. It's really the same equation 3 times by changing those labeling. Okay, nothing different. So this is basically what you can do to be able to solve problems for non-particle objects. But again, the key thing is you can only do that for center of mass point. Next, we are going to talk about linear momentum.